So thank you very much for having me. My name is Ronja Billenstein. I'm a PhD student of Sebastian Höhner at the LMU Munich in Germany, and I work on combining diffusion approximation and Bayesian skyline plots for inferring demographic histories. And as Rui said, I will present a poster in tomorrow's poster session, which looks like this. And I thought I could use the flash talk to make a quick walkthrough of my poster. So let's start with a little bit of background. Imagine you have snipped data from one population and you represent it in form of a site frequency spectrum, and you wonder why your site frequency spectrum has this specific shape. And the reason for this might be that there's a very specific underlying demographic history. For example, your population could have had a constant population size through time, or it might have experienced exponential growth towards the present, or any other curve that you can imagine. So now you would like to have a software to analyze your site frequency spectrum or the shape of your site frequency spectrum to give you the underlying demographic history. And as you might know, there already are some approaches to do this, and I would like to focus on one specific method for a moment, which is DADI. DADI is diffusion approximation for demographic inference. It was first introduced by Ryan Gutenkunst et al. In 2009, and it gives you a maximum likelihood estimation of your demographic history. But depending on what you expect from your inference software, there are some issues. The first issue is flexibility. In DADI, you need to pre-specify the demographic scenario you would like to analyze. But maybe you would prefer to have one function applicable to all possible demographic scenarios without the need to decide beforehand which one it might be. And another possible issue is that DADI doesn't give you an estimate of uncertainty. So if you're, for example, interested in the credible intervals about your estimate, DADI doesn't give you those. So we wanted to incorporate the diffusion approximation approach into a framework that's more flexible and allows for the estimation of uncertainty. And we chose a Bayesian skyline plot to do so. A Bayesian skyline plot applies a piecewise constant model of population size. And this is just a very reduced depiction of how our approach looks like. You have input parameters. You need to decide on how many epochs you think are applicable to your data. Let's say, for example, you want to analyze 5 different epochs with 5 different population sizes. Then you put this into our framework. Then a model site frequency spectrum is calculated for your 5 epochs based on diffusion approximation. There is a likelihood calculation where this model spectrum is compared to the site frequency spectrum from your data. And all of this happens within an MCMC framework. So there is, for example, an accept reject procedure happening that I didn't depict here. And then you change the parameters of your site frequency spectrum. So you change the population size for your 5 epochs and then do the same again. And you do this for a specific number of steps. And in the end, you get the distribution of your site frequency spectrum parameters. So for each epoch, you get a distribution of the population size in that epoch. And you can summarize this in a Bayesian skyline plot, which is why we called our method diffusion Bayesian skyline plot, or short DBSP. We already have some very first results. We did simulations with a constant demographic history with a constant population size of 50 for 50 samples and 10,000 loci. And then we did an analysis without DBSP with 1 epoch. And as you can see here, the resulting population size for this epoch is very similar to our original 50. And we also have the credible intervals. So this is basically where we're at right now. And for the future, the next step will be to implement the DBSP with more epochs for simulated data with various demographic histories. For example, with an exponential demographic history, and we could do an analysis with 10 epochs. And of course, we would also like to apply our approach to empirical data afterwards. And this plot is just a very quick preview of what such an analysis can look like. Here we analyzed the same data as on the slide before, just with 2 epochs, and you can see that we still get a very good estimate of the population size with a small shift at 0.5, which is where the epochs changed. And with that, I would like to thank all the members of my lab, especially my supervisor, Sebastian Höhner. We're associated with the Paleontology and Geobiology and the GeoBio Center of the LMU Munich. And I was funded by the SP1991 program from the DFG and by the Emulator program. So thank you all for listening and thank you for having me. And I'm happy to discuss all of this tomorrow.